So let's look at a problem to understand the application of the heat diffusion equation and how to use the boundary conditions and initial conditions to find the temperature distribution in different bodies. So for this particular problem, we have to find the temperature distribution in a wall at steady state. So this is the wall that we have, which has a thickness of L. So we have x is equal to 0 right here and x is equal to L right here. The surface temperature at x is equal to L is TL, which is known. There is convective heat transfer between the surface at x is equal to L and the wall, and we know the temperature of the surrounding T infinity and the convective heat transfer coefficient, and it's shown that heat is being transferred only in the positive x direction, so it's a one-dimensional heat transfer. So this is the heat diffusion equation that we had derived, and we can write this either in a 3D space or in a 1D space, and we've seen how the equations look like. So before whenever you start doing a problem, the first thing that you must write down is you should write down the assumptions. So our first assumption in this problem is that this is a one-dimensional heat transfer problem. So your heat is just flowing in the x direction. The second assumption that we have, and it's given, is that our system is in a steady state. That means that your temperature is not changing with respect to time. The third assumption that we have, or that we are going to assume, is that the properties, the thermal properties, are constant. Now what I mean by constant is that these thermal properties can be a function of x or temperature, but for simplicity and just to understand the fundamentals of how to solve the energy transport equation, we'll assume that these thermal properties rho, Cp, and the thermal conductivity are constant, so that we can remove this out of the derivative. So our third assumption will be constant thermal properties. And the fourth example is about heat generation. So this should be triple prime. It's not a heat flux, it's heat generation. So our fourth assumption will be that because it's not mentioned in the problem statement or in the figure given, we'll assume that there is no heat generation. Okay. So these are our four assumptions. Now what do we know? What's given in the problem? So we know the temperature of the surface at x is equal to L. So the first thing that we know is that temperature at x is equal to L is TL. The second thing we know is that there is convection at x is equal to L, and T infinity and H are known quantities. So these are the two things that we know, and they'll help us in simplifying the heat diffusion equation. So how do we use the assumptions and the things we know to reduce this heat diffusion equation into a simplified form and find the temperature distribution. So the first thing that we know is that the system is at steady state. So this term here will go to 0 because it's at steady state. There's no heat generation, so our Q triple prime will go to 0 as well. So this will, and we just have conduction in one direction, and that's the x direction. So our heat diffusion equation will reduce down to the derivative of k times dt by dx with respect to x equals to 0. And let's say this is our diffusion equation. This is our 1D diffusion equation at steady state. Let's say it's equation 1. Now to find the temperature distribution, we need to integrate this twice, right? Because it's a second order differential equation, we need to integrate it twice, and we will get two coefficients of integration, and we'll use the boundary conditions to find the values of those coefficients. So let's integrate this. So on integrating the left hand side and right hand side, we get k times dt by dx equals to some constant c1, because your right hand side was 0, so you'll just get a constant c1 on your right hand side. Now integrating this equation again, we get, let's write it properly. So let's say it's k dt equals to integration of c1 into dx, which will give us k times t equals to c1 times x plus another constant of integration c2, and here our temperature will be a function of x. Okay, so we have two unknowns, c1 and c2, and we need to solve for them. And to solve these two unknowns, we need two equations. And where will we get those two equations from? Our boundary conditions. So we have two boundary conditions. Okay, the first boundary condition is temperature at x is equal to L, not 0 but L, is equal to TL. Now let's see how we can apply this boundary condition and find the value of a constant. So let's substitute x is equal to L and T equals to TL in the equation that we have. So this will give us k times TL equals C1 into, substitute L with x with L, sorry, plus C2, or we can write this down as C2 equals to C1 times L minus, or let's do it the other way around. So this will be k times TL minus C1 times L. And let's say this is our equation 2. Okay, so we got C2 as thermal conductivity times TL minus C1 times L, and we still need to find the value of C1. So for that we'll use our second boundary condition, which is this conduction in one direction, so which says there's convection at x is equal to L. And how will you write this down? You will write this as minus k times dt by dx at x is equal to L equals h into t infinity minus TL. So we know h, we know T infinity, we know TL, and K is the thermal conductivity. So let's take the original equation that we have and the equation that we found out for temperature in terms of C1 and C2 and substitute it in equation 3. And what we'll get is we'll get K into the derivative of C1 into x upon k plus C2 upon k, right, equals h times T infinity minus TL. Now we see the k is cancelling out, and we have to find the derivative of this at x is equal to L. So this will turn out to be minus C1 and the derivative of x will be 1 plus 0 because the derivative of a constant quantity is 0 equals h into T infinity minus TL. So here we have our second constant, the value of our constant C1, which is minus h times T infinity minus TL. Okay, so we'll use the value of C1 and substitute it in equation 2. So let's use a different one for that. Use C1 from 4 in equation 2. So our C2 will now be K times TL minus h times T infinity minus TL times L. So our C2 will be K into TL plus H L into T infinity minus TL. And this is how we find the two constants. So let's substitute these values into the equation that we found out for temperature distribution and see how our temperature distribution will look like. So we have our two constants C1 and C2 as minus h times T infinity minus TL and C2 as K into TL, that's the temperature at x is equal to L, plus h into L multiplied by T infinity minus TL. And the equation that we had for temperature T of x was C1 times x plus C2. So let's substitute C1 and C2 and let's see what we get. So this will be TL times x plus K times TL plus h times L into T infinity minus TL. Okay, so our temperature distribution in this particular wall will be it will be h by k into T infinity minus TL times, sorry, this will be L minus X plus TL. So this is how your temperature distribution equation will look like, and then you can substitute any value of X and find the temperature at that particular X. So let's test if this equation is correct. So let's see. So let's use a different color. So at X is equal to L, we should get temperature as TL. So if you put in X is equal to L here, this term will go to 0, and your T of X will be equal to T of L. So it checks off. Okay. So this is how you solve for temperature distribution using the given boundary conditions and assumptions.